In this lecture, we would like to present trigonometry in its most compact form, with a minimum of memorization. Imaginary numbers will be a brief preliminary step. Here's the algebra that we'll need for this. What's called the distributive law. Combination of operations here. We will also use a property of exponents. Two powers of A multiplied together, add the exponents. Finally, we'll need the Cartesian plane. That's a way of representing two-dimensional phenomena. Got a pair of number lines there, x and y axes. Mark off numbers on each of those axes. The dot you get with those x and y values called an ordered pair, A, comma, B. Imaginary numbers arise when you try to take the square root of -1. Let's give it a generic name. X is very popular. This means x squared is -1. Let's add 1 to both sides. I claim there's no real solution, no real number x that satisfies that equation. The problem is that when you square a real number, let's say we imagine x is real. When you square a real number, you're going to get something non-negative. Here are the possible values of x squared. Then we're adding 1. That's going to shift that shaded stuff over to the right. There's where x squared plus 1 is floating around. Notice that there's no way this shaded area can include 0. I see failure. Failure at solving this equation, x squared plus 1 equals 0. At least if x is a real number. We are not deterred by this failure. We really want that square root of -1, so we'll make up a name for it. It doesn't exist, give it a name. We choose the letter I, lowercase I. That's short for imaginary. Not real. I is the letter for a number whose square is -1. Written in symbols, that's I, square root of -1, or square both sides, I squared equals -1. We'd also like to multiply I by real numbers. Say you have a real number A. A times I, anything of that form, will be what we call an imaginary number. For example, one over square root of 3 times I. That's an example of an imaginary number. Watch what happens when we square this number. That means you square each part. The 1 over root 3 squared is 1/3. The I squared, we already know, is -1. In other words, a negative real number, negative 1/3. The imaginary number we started with is the square root of negative 1/3. That's what all imaginary numbers look like. The square root of a negative real number. That's the imaginary number part of this lecture. The trigonometry part that I promised you. That's going to be a single picture involving what's called the unit circle. The unit circle is a subset of the Cartesian plane. We're talking about ordered pairs, x comma y. It's ordered pairs such that when you add their squares together, you get 1. We're talking about a circle of radius 1, centered at the origin. Let's mark off some of the most obvious points on the unit circle. Up there at the top, the ordered pair 0, 1. The right extreme, furthest to the right, 1, 0. Over here on the left, negative 1, 0. Down here, 0, negative 1. Over here, I'll put the single picture that we need for trigonometry. Then on this other board, I'll tell you what all the symbols mean. Here's the Cartesian plane. There's the unit circle. Radius 1. And part of this picture is the following peculiar looking equation. That equation has a name, Euler's formula. And we might as well include on our picture a reminder of what that letter I means. I squared equals negative 1. This peculiar letter here is a Greek letter called theta. That's the spelling. Phonetically, theta. The COS is short for cosine. The SIN is short for sine. The more complete statement here, COS theta, that reads cosine of theta. It's not multiplication. You think of it in a more physical way of applying cosine to the letter theta. Likewise for sine theta, SIN theta, that reads sine of theta. And then the lowercase e. That is a certain real number, fixed always, as a fixed value. I'm not going to tell you what it is. At the end of the lecture, we'll have a reference for everything, including E. But for this lecture, it actually doesn't matter what its value is. Just that it's there. Just that it's sitting there in Euler's formula. So, quick summary. Ordered pair, cosine theta, sine theta. That is a point on the unit circle such that this counterclockwise arc, starting at 1, 0, ending up at the cos theta, sine theta, that arc that I drew arrows around has length theta. Let's do some examples. Let's say we wanted cosine and sine of 2 pi. The number 2 pi. To match this picture, first thing we got to do is mark off that length of 2 pi on the unit circle. Well, we're talking about a circle of radius 1. That 2 pi you might recognize as the circumference all the way around what? Starting here at 1, 0, we started looping around the outside. And after all that traveling, we ended up back where we started. That's 2 pi. If you snipped this thing with arrows on it and straightened it out, that would be length 2 pi. So there we are. There's the cosine and sine of 2 pi. Notice that we actually get both pieces of information at once. Equality of ordered pairs means the first coordinate has got to match. So we know that cosine of 2 pi is 1. And the second coordinate, sine of 2 pi, has to be 0. Definitely some economy here. 2 things at once. Even if you only cared about the cosine, you would unavoidably get the sine at the same time. And while we're here, we might as well see what Euler's formula has to say. Let's see, e to the I theta, let's squeeze it in here. Theta here is 2 pi. E to the I, 2 pi. First we write down the cosine of 1. Then we want I times the sine. In this case, I times 0. Anything times 0 is 0, even mysterious things like I. So we appear to be finding out that e to the I 2 pi is 1. That was 2 pi. Let's try pi. Cosine and sine of pi. First step is always to locate that value of pi on the unit circle. That sounds like half a circumference. The full circumference is 2 pi. Pi is going to be 1/2 of that, like the upper half of the unit circle. Radius 1. Upper half only to get a length of pi. End up right there. That point right there will be cosine pi, comma, sine pi. We just have to recognize that point on the unit circle. That has an x-coordinate of -1 and a y-coordinate of 0. Once again, we've gotten both the cosine and the sine at the same time. Cosine turned out to be -1, sine 0. I can't resist throwing that information into Euler's formula. That would be e raised to the I times pi power. We put down the cosine, the -1, plus I times whatever the sine is, just 0 again. E to the I pi is -1. Let's do another halving. Cutting in half, I mean. Let's look at sine and cosine of pi over 2. Now we're talking about a quarter circle. Pi over 2 is 1/4 of 2 pi. Quarter circle, starting at 1, 0, that puts you up at the top of the unit circle. Those coordinates are 0, 1. Whatever they are, since we've identified the right point, that'll be giving you cosine pi over 2, comma, sine of pi over 2. Euler's formula, we can't resist. Plunk down the cosine of pi over 2, that's 0, plus I times the sine of pi over 2, that's 1. This time we're getting an imaginary number for the exponential. I really have to put a bracket around this. There's a combination of all the strange numbers we've seen. Pi, that's a strange one. I, definitely, it's not even real. And the mysterious letter, number E. That deserves to be on a t-shirt. That's the sort of message the right kind of person could wear with pride. All the numerical mysteries put together. While we're at it, let's mention explicitly what cosine and sine are. Remember that you get the cosine from the first coordinate. Cosine of pi over 2 is 0. And second coordinate, sine of pi over 2 is 1. Let's draw a single picture to put down all the sines and cosines we've gotten so far. Everything's on the unit circle here. Starting at 1, 0, we found out that's the cosine of 2 pi, comma, sine of 2 pi. It's actually more than that. In this general definition, imagine you shrunk theta. You started squeezing theta down to nothing. Smaller, smaller, smaller. When you squish it to nothing, you're back at 1, 0. So there's another cosine and sine. That same ordered pair, 1, 0, it's not just cosine and sine of 2 pi, it's cosine and sine of 0. This is going to happen a lot. Every point on the unit circle actually comes from infinitely many sines and cosines. That'll be a good thing. We're going to find out that that's a very worthwhile thing to occur. Let's travel around counterclockwise. Here's the point 0, 1. That'll come from pi over 2, sine and cosine. Let's keep moving counterclockwise. Here's the point negative 1, 0. Remember, we got that from arc length of pi. That's cosine and sine of pi. This one we haven't actually done. I'll leave it to you to do the geometry you need to notice that the point 0, negative 1, that looks like an arc length of 3 pi over 2. 3/4 of the way around the circle. Cosine sine of 3 pi over 2. Notice the sense of motion that you get as you calculate these sines and cosine. As theta increases, 0, pi over 2, pi, that causes us to move counterclockwise. So this is all for theta increasing. And so on. Maybe I don't want to get carried away. In particular, if you let theta go from 0 to 2 pi, that'll take you all the way around the unit circle. We started out at 1, 0, traveled around, and ended up back where we started. That's theta going from 0 to 2 pi. Having performed this circumnavigation, why should I stop? Here's the unit circle. Let's put our traveling over here. I'm not being completely accurate here. The motion is actually on the unit circle, but I need a little separation. Traveling, traveling, traveling. There's theta equals 2 pi. And I say to myself, I don't want to stop. I've got all this momentum. I'm going to continue going counterclockwise around the unit circle. Imagine my finger is doing the traveling. Starting here, counterclockwise, counterclockwise, counterclockwise. For example, let's say we wanted cosine and sine of 3 pi. What's relevant to me is that 3 pi is 2 pi plus pi. That tells me, when I stare at those numbers, that tells me that first I make a complete revolution, a full circle, and then the plus pi tells me to make, in addition, an extra half circle. Travel, 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 travel. There's the 2 pi. But I'm not done. Then I add on an extra pi. An extra half circle. Now the 2 pi had no influence at all. It just took us back where we started. We've lost all memory, all consequences of that traveling. All that's really making a difference is that final half circle pi. That sure looks familiar. We're back there at -1, 0. That's the corresponding point on the unit circle. So that's going to give us our cosine and sine. Cosine of 3 pi is the -1. But that's actually the same as the cosine of pi. Same cosine. We already calculated that one. And sine of 3 pi equal to 0. The same as the sine of pi. So counterclockwise motion that corresponds to increasing theta. Increasing theta spins you counterclockwise around the unit circle. That means the clockwise motion think opposites now. The opposite of counterclockwise, that's going to undo. That's going to cancel out the increasing theta. Clockwise motion corresponds to decreasing theta. Let's make a sketch like we did in this picture, except go in the opposite direction. Same old unit circle, start at 1, 0 as usual, but now move clockwise a distance theta. The corresponding cosine and sine will be applied to negative theta. Because of the clockwise motion. For example, let's travel a distance pi over 2 on the unit circle, but clockwise. Starting at 1, 0 always. Pi over 2 is a quarter circle, so that takes you down to here. Arc length pi over 2, clockwise. There we are down at the point 0, negative 1. That's giving us cosine and sine of negative pi over 2. And as usual, we can pull out the separate cosine and sine. Cosine of negative pi over 2 is 0. Sine is negative 1. Now, part of what makes these cosines and sines of interest is certain properties that they have. I'm going to do some of these as examples, but they are far from the only ones. Let's say you are interested, for example, in theta versus negative theta. As we were just talking about, I'd like to get a very general relationship. There's actually a very strong statement you can make about theta versus negative theta. Everything relies on getting a good picture, at least a chunk of the unit circle. Oh, let's say we put theta right about here. There's a length of theta. There's cos theta, sine theta. Negative theta means the same length, but in the opposite direction. The way to get that same length is to drop a perpendicular. Reflect this point through the x-axis, like so. It's like taking the mirror image of this picture. X-axis is the mirror. Flip that whole picture over. Now what we're getting here, we know, is going to be cosine sine of negative theta. We were just talking about that. But now stare at this picture we drew. When we reflected through the x-axis, the cosine is going to stay the same. It's still cosine theta for the x-coordinate. The y-coordinate, because of that reflection, got negated. The y-coordinate of this point is the negative of the upper y-coordinate. You're going to get a negative sine theta. Pulling out the cosines and sines separately, this will be formula number 1, property number 1. The cosine of negative theta appears to be cosine of theta. Negation changed nothing there. But the sign definitely got changed. The sine of negative theta comes out to be negative sine theta. That's a proof by picture. You're actually deducing these cosine and sine formulas. No one has to tell you. You can figure them out yourself by drawing this picture. The next relationship I'd like to look at is theta versus theta plus 2 pi. Always challenging to get a neat picture. Let's put theta over here, say. Adding 2 pi means beginning at this point. Make a full circumference around the circle. I better give myself more room. Let's move theta over here. Okay, here we go. starting at 1, 0. There's the theta mark. Starting from there, starting at that point, full circle. We ended up at the same point. The theta plus 2 pi brought you back to the same point as theta. A little extra dizziness. That's the only difference I could see. Maybe that circumnavigation was disorienting, but when the dust clears, things look awfully familiar. What I'm seeing here is that the ordered pair we got from theta, that's right here, that's the same ordered pair that you get from theta plus 2 pi. Let's call that formula 2. Same thing happens with cosine and sine. Cosine stays the same when you add on 2 pi. Likewise for sine. This is a very useful property. It's given a name. The name for this is that sine and cosine are periodic. Periodic means repeating yourself. We'll come back to this later. Now, one thing to worry about, at least I worry about it for myself, will my artwork be tidy enough to give me useful information? It doesn't have to be great. You don't have to have a perfect unit circle, nothing like that. Still, I'm not sure I trust my art ability. You might find it reassuring that you can get the same result entirely without drawing a picture. Let's call this the algebraic approach. This is often a choice in math. You can be visual, meaning drawing pictures. That's what geometry is about. Or you can be algebraic, meaning calculations. It's a tough choice. Algebra is precise, that's its advantage, but often intuition is missing. Pictures like this, I think, have a nice intuition, but there's always that risk. There's always that insecurity that maybe my hand shook at the wrong moment. What I mean by algebraic here is Euler's formula. Let's see, we're starting out, we want to worry about cosine and sine of theta plus 2 pi. We can patch those two together using Euler's formula. The cosine plus I times the sine. In this case, applied to theta plus 2 pi. Euler's formula puts those together into that single peculiar exponential. E to the I, parentheses, theta plus 2 pi. Let's distribute the I through. We've got in the exponent I theta plus I 2 pi. There's the exponent law that I need. Adding the exponents corresponds to multiplication down here at the E level. E to the I theta times E to the I 2 pi. Now there's a spot of good news. That's one of the exponentials we actually figured out. It turned out to be the number 1. E to the I 2 pi. That's a number we know. It turned out to be 1. So we're back to E to the I theta. Let's apply Euler's formula again. Cosine theta plus I sine theta. In order for this number here to match this number here, each part has to match. The part that's untouched by I, those have to be equal. And the parts that are attached to the number I, those have got to be equal also. That's another way of getting the same approach. It comes from a different side of this picture we drew, the Euler's formula side. Next, I'd like to look at theta versus theta plus pi. Let's say theta put us right here. That would be an arc length of theta. The plus pi means traveling a half a circle. Half a circle has got a base on it. You can get that base here by reflecting through the origin. If theta takes you up to here, then an extra pi, that would go along like this. Half a circle. Or to get the entire picture, the theta plus pi is occurring right about here. That'll be cosine of theta plus pi, sine of theta plus pi. That's down here. We reflected through the origin from that dot, cos theta, sine theta. reflecting through the origin has the effect of hitting each coordinate with a -1. The theta plus pi, cosine and sine, corresponds to negative cos theta, negative sine theta. Or, if you look at individual sines and cosines, what are we up to here? That's formula 3. That's cosine theta plus pi equals negative cos theta. Likewise for sine. Let's try to get the same result the algebraic way. Maybe I'm not feeling so visual. I'd like the security of a calculation. Algebraic here means Euler's formula. This one. Sine and cosine of theta plus pi we put together. Euler's formula puts those together into a single exponential. Just like we did with 2 pi, that becomes a product of exponentials. E to the I theta times e to the I pi. Good news again. There's an exponential that we actually know the value of. That turned out to be -1. Using Euler's formula, but multiplying through by -1, you get negative cos theta plus I times negative sine theta. And just like with 2 pi, for these two things to be equal, the stuff without the I has to be equal, and the stuff attached to I has to be equal. Let's see, so far we've been adding pi or 2 pi to theta. I'd like to do something much more ambitious now. Add an arbitrary extra number to theta. I'd like to get sine and cosine. Theta plus psi. That's another Greek letter, psi. That's how it's spelled. Phonetically, I would spell it S-I-G-H, psi. I better put a question mark here, because we never know. Perhaps we'll fail to get anything. Let's be humble right from the beginning. Here I definitely prefer Euler's formula. Applied to theta plus psi. Those become a single exponential. Exponent law again. That sum in the exponent becomes a product of exponentials. So more complication here because neither of these is recognizable. We're not just going to get a plus or minus 1 here. What we want to do here is apply Euler's formula to each one of these exponentials. First, you've got cos theta plus I sine theta. That's the e to the I theta. Then the e to the I psi. This is where the distributive law is going to be a big deal. I'm going to leave the calculations to you. The traditional symbol for this sort of cop-out is 3 dots. It means I trust you. It's not a bad thing. Mostly we're talking about the distributive law applied twice. And after you apply the distributive law, things will simplify very nicely when you remember that I squared is just -1. Let's write down what the conclusion of all this is. We can only find room. Inside brackets here, I'm going to write down the stuff that don't involve I. Inside the first brackets, cos theta, cos psi, minus sine theta, sine psi, then we put everything that's multiplied by I in a separate set of brackets. Cos theta sine psi plus sine theta cosine psi. So again, you're getting 2 things simultaneously. All this stuff here, that's the cosine of theta plus psi. All the stuff in the second set of brackets, that's the sine. That will be formula 4. Properties of sine and cosine. So email me if you get something different when you apply the distributive law. Formulas 2 and 3 are special cases of this. That was where we were adding on pi or 2 pi. Here's another special case. Let's say we add pi over 2 to theta. In other words, that's the psi in this formula for cosine. Looks like we're getting cos theta times cos pi over 2 like here. Then we're subtracting sine theta sine of pi over 2. The good news is that this turned out to be 0, cosine of pi over 2, and this one turned out to be 1. We are ending up with negative sine theta. A similar calculation that I'll leave to you, just say similarly, the sine of theta plus pi over 2 turns out to be the cosine of theta. Let's call this formula 5. It seems peculiar that sine and cosine are so closely related. We just shifted the angle a little, sine changed to cosine. There's an equally popular relationship between sine and cosine. It emerges if you just remember that that ordered pair is on the unit circle. Unit circle, remember, sum of the squares equals 1. So my reasoning here is just to notice that this ordered pair is on the unit circle. That implies, let's give this a number, formula 6. That implies that the sum of the squares, cos theta squared plus sine theta squared, have to add up to 1, just to be on the unit circle. I want to go back to the property that we called periodic. Or periodicity. I'll just state it for sine. When you add 2 pi, you get the same sign. What this means in terms of the graph, what this means is that if you draw the graph of sine only between 0 and 2 pi, theta between 0 and 2 pi, let's mark off pi over 2 pi and 2 pi, horizontal axis. Turns out to look like this. The periodicity forces that graph to replicate itself infinitely often as theta goes to plus or minus infinity. Let me give myself more room for this graph, this piece of the graph so far. And then we'll do the enlargement that you get from being periodic. There's the piece we started with. Make a copy of this, paste it on the right. Don't stop there. Make another copy, paste it on. We've run out of room. So 3 dots means keep going to the right off the chalkboard. You know, this thing has gotten stretched out a little too much. Let's try to trim this down to size. Remember, we're making exact copies of that one piece of the graph. Artistic limitations are the only limitations here. And also to the left, make it repeat. That looks like a wave. Anything in the physical world that repeats itself like that looks like a wave. Sound, that comes in waves. Light. Light is actually a special case of what are called electromagnetic waves. Very peculiar phenomena. Alternating electric and magnetic fields. Oscillating at the same frequency. Very peculiar fundamental discovery. About 150 years ago. The number of hours of daylight, that's another case of a sine wave. Hours of daylight in a day. In general, there are slight perturbations of just y equals sine of theta. Here's the most general equation for a wave. Put a capital A in front, and inside the sign, I'm going to throw in some extra Greek letters. Let's see. 3 of these letters are fixed. The capital A, that letter's called a gamma, I believe, and psi. For a given wave, those are just fixed numbers. Theta is the variable. The A stands for amplitude. The gamma, at least when you divide by 2 pi, is frequency. The psi is a phase shift. That just means moving the graph to the left or right. Let me make rough sketches of what amplitude and frequency look like. Here's a large amplitude. And here's a relatively small amplitude. We're talking about how tall the graph is. Very tall, very short, very tall, very short. That's amplitude. Frequency. Here's a large frequency. And here's a small frequency. Frequency measures how jittery the graph is. Up, down, up, down, up, down. As opposed to a slow, calm oscillation. Now this becomes particularly interesting when you look at particular classes of waves. Let's talk about those electromagnetic waves first. The frequency tells you what kind of wave you get. I'll put these in order. I'll put these waves in order of increasing frequency. Starting with visible light. Red, that's the smallest frequency. Orange, yellow, green, blue, and violet. Those are the colors you'll see in that order if you reflect light through a prism. Sometimes you find these prisms occurring naturally. A ray of light will land on your floor in such a way that this is the order of the colors that will appear. So violet has the highest frequency. If you make the frequency higher than violet, that's called ultraviolet. We can't see it. Our eyes are defective. We can't see ultraviolet light, but we can feel it. Mainly, you can get a sunburn from ultraviolet light. Can't see it, but it's doing things to you, to your skin in particular. Higher frequencies, you get eventually to X-rays, those things that show off your bones in a doctor's office. Higher frequency than that, what are called gamma rays. X-rays are eventually damaging. Gamma rays are a lot worse. They get more inside and they can do more damage. Sound has, well, for sound, we're going to see the effect of both frequency and amplitude. It takes on a very tangible form. The amplitude corresponds to volume. The bigger the amplitude, the louder the sound that you're going to get. And the frequency corresponds to pitch. The higher the note, the higher the frequency. Notice that there's been no mention of geometry so far. But the story is that when you look at this unit circle in a little more detail, you will see a right triangle buried inside it. Let me see if I can draw that. Let's say here's an arc length of theta. So this ordered pair, remember, is cos theta sine theta. That means if you drop a perpendicular down to here, right angle there, draw this line here, the height is the sine of theta, and the base of that triangle is the cosine of theta. And the angle here, a very successful custom is to measure that angle in terms of that corresponding arc length. This is a type of angle measure called radians. Let's pull out that triangle so we can focus on it. Remember, the radius is 1, so this hypotenuse is going to be 1 also. One leg is sine theta, the other leg is cosine theta. Now, if we expand that right triangle, keeping all the ratios equal, so keep that angle there. That'll keep the ratios equal if you hold on to the same angle. Call these sides A, B, and C. If you look, for example, at B divided by C, that corresponds over here to sine theta divided by 1. Dividing by 1, we can do in our heads, does nothing. The popular way to describe that ratio is opposite over hypotenuse. Likewise for cosine. If you look at A over C, that corresponds to cosine theta over 1. There's cosine of theta, popularly called adjacent over hypotenuse. This is a fairly natural way to attack geometry. Start with the trig that we've been outlining. That gives you powerful tools for getting going with geometry. Okay, I'll stop there. after putting up an advertisement for more details about what we've been talking about.